Here, in the Computer Graphics Laboratory within the Control and Instrumentation Group of the Department of Electronic and Electrical Engineering at Salford, work is carried out developing computer-aided design tools to assist the engineer, in particular the control engineer, in his pursuit for successful, right first-time design. I'm Clive Downes, and I'm going to present just such a computer package. It's called SATRES, which is an acronym for the Modular Time Response Method. This is, in fact, a computer program allowing the control design engineer to input and analyze a complex sampled data control system using fairly powerful graphical aids. And for this, we obviously need a fairly powerful piece of equipment. So we've got an ICL PERQ here, which has its own associated graphics display. And for input, we have a tablet. And for taking offline hard copies, we have a plotter and a printer behind me, which is useful because then the engineer, at a later date, can analyse his work at his leisure. Upon startup, the program asks for information concerning the peripherals to be connected and the types of graphics windows to be used. With this done, the user is then interrogated about the control system he wishes to analyse, either pulling a data file in from the internal file store, or as in this case, a new entry is going to be made. We then move on to enter the system itself, which is, in fact, simplicity itself. So we select Start, and using the tablet, we position our first node. And then choose a module. Say, we have an input here, and we position it. In specifying a control system as a signal flow graph, it is broken down into a signal flow path, interlinked by independent modules connected by nodes. Well, these modules may represent inputs, pure and dynamic gains, non-linearities of various types, and finally samplers. And the nodes which connect all of these modules may or may not be summing nodes. And so on, we complete the system. This, in fact, continues until the topography of our system is complete. And then we choose to take a hard copy, say, with the results being output at the plotter, which we then use to reference, or we can file it away. We could, at this stage, go back and either delete or modify the topography or parts of it. However, we'll presume all is well and continue and define the modules. At this point, the program goes through its modules and asks for the parameters and characteristics which define these modules. For instance, we'll have a step input of 10 units here. As the program, when running its simulation, samples the input of each module for a given time instant and produces an output over the time increment using simple state transition matrix operations, with the inputs being taken from the corresponding send nodes and the outputs being accumulated and stored at the receive nodes, well, then it can be seen that the modules are defined independently from one another, which is the beauty of this method, as a great degree of flexibility is preserved. However, it is an approximation requiring a careful choice of the time increment. So, having specified all the modules and a record taken, we've completed the signal flow graph input. All that remains to be done before we enter the simulation is enter the time increment. Tell the program which modules to process first when a conflict occurs, as around a sum injunction. We do this by pointing at the modules and put them in order. We then enter the number of time steps for which we want the simulation to run. And finally, we select the nodes whose responses we desire for analysis. We'll have nodes 2, 5, 6, 7, say. After computation, we're now able to view the responses of the selected nodes, or just one node, say. And we can keep a record and add this to our file. And we could return to the main program to either modify the signal flow graph or enter a new one. So selecting Help brings up the Help window. And we can see what we want to do. Okay, let's go back to the original point where we specify the system topography, SFG. We could add an additional input, say, which will become R3. Now we have a new set occurs for this altered control system. Okay, let's return again and we'll say that this run is complete. We can also analyse more complex systems, as was this system filed on disk, which we'll read in, this having multiple inputs and more complex loops. This example is in fact dealt with in exactly the same way as the previous example. And so we have it, the end of another run, and a set of results for the engineer to analyse. Here we have, in fact, a powerful means to allow the control engineer to analyse complex control systems in a time, efficient and reliable manner. And what's more, as the program itself is written in FORTRAN and given a suitable graphics package, which in this case is our in-house design, we can make the program as portable as possible. And indeed, the original version of the program is already running on the department's Prime 550 computer in conjunction with the Tektronix graphics terminals. And this is just one of the packages being developed here.